Hello, everyone. Welcome to our talk on time series forecasting and anomaly detection with BigQuery ML. So before we start, it's okay if you're not familiar with Google BigQuery because we will quickly go over the product in our talk later on. It's also okay if you're not familiar with BigQuery ML because we will delve into the specifics about BigQuery ML in our talk today as well and take you through step-by-step how to do time series forecasting and anomaly detection very easily using BigQuery ML. My name is Stephanie Wang. I'm a DRE at Google Cloud. I primarily focus on maintaining and developing the Google BigQuery Java client libraries. You can follow me on Twitter at StephWangBuilds or check out my work on my website at StephWang526 at github.io. Today, I'm also very lucky to have Polong Lin with me to present together.
Hi, everyone. I'm Polong. I'm also a developer relations engineer with Google Cloud. My focus is on data science and machine learning. And as just for those who are unaware of what a developer relations engineer exactly is, our goal is to help data scientists, data analysts, developers out there make the most of Google Cloud. And so we kind of teach best practices, and we also give feedback back to the product team. So that's a little bit of an overview of kind of what we do at Google. Okay, go ahead, Stephanie.
Awesome. Thank you so much, Polong. So time series forecasting, I'm sure everyone here is somewhat familiar with the applications of what it can help to do. So here are some examples of how time series forecasting can help drive critical business decisions. In retail, for example, demand, sales, or inventory levels forecasting could help business owners decide how much inventory to purchase and stock so that they can avoid either over or under allocation of resources, which can translate into revenue loss. In workforce management or workforce planning, support tickets or support calls, store traffic forecasting can help business owners decide on store operation hours or the number of staff to hire so that they can minimize idle paid hours and also maximize revenues. In utilities, the ability to predict energy or commodities demand can help drive decisions on resource allocations. And in the travel industry, the ability to predict hotel occupancy and flight bookings is very critical as well in making sure that customers' needs can be met and can be satisfied. The list goes on, right? The point here is that the ability to forecast accurately and promptly will soon become a necessity to stay competitive in any industry. So,
go ahead.
Go ahead.
So when it comes to doing time series forecasting, if you have maybe just a couple of, let's say, products or items or things you want to forecast, maybe it's very easy to manage the infrastructure, any kind of software that you might need to do your forecasting. But when it comes to doing forecasting at a very, very large scale, so we see some people forecasting millions of products across lots and lots of stores. And when you get to that level of scale, the sort of infrastructure that you need to set up and to maintain can become quite overwhelming. So first is, where is your data stored? And then how do you do forecasting on top of that? Whether you need to export your data outside of wherever your data is stored and then do your forecasting, or figuring out how to work within different teams between people who are storing the data and people who are analyzing data, or people who are building these models. It can get quite complex as the number of things that you need to forecast grows, and as the company is larger and as teams become larger, this can become quickly quite overwhelming. So in the next slide, I want to kind of give you an overview of what we call Google BigQuery on Google Cloud. This is essentially a data warehouse for enterprises on Google Cloud, and it is designed to be incredible at scale. So just as a quick example here in this animation, in this GIF, you can see here within just 5-6 seconds, over 500 gigabytes were processed in this fairly non-trivial SQL statement. So the data is stored in BigQuery. We're running a SQL query, And then all I have to do is just click on the run button. And by clicking on the run button, it'll figure out exactly what's needed to be able to analyze this data. So it analyzes 500 gigabytes or over 500 gigabytes in just 5.6 seconds without me as a user having to worry and figure out how do I set up, all the clusters or CPUs or anything in the back end. I can just focus on the analysis. So that's the kind of scale that we're kind of talking about, trying to minimize the amount of time to get to the insight once you have your data. And so the question here becomes, how do we then do forecasting based off of data that's stored in such a way in a data warehouse on BigQuery? So that's where we can talk a little bit more about BigQuery ML in this next coming slides. So BigQuery ML is the machine learning functionality that's built into BigQuery directly. And so what that means is you can just use SQL to train and deploy machine learning models, including time series forecasting as well. So without having to move your data outside of BigQuery, so you don't have to export your data and then try to figure out, where are all my copies of data. You can keep your data in BigQuery, run your SQL statements, and train your machine learning models and use them in production as well, without having to kind of worry about all the infrastructure that you may need to set up. Maybe you don't even need extra hands to be able to figure out how do you do machine learning. You could do it yourself if you're already familiar with SQL. So we kind of want to walk you through this today, but just to give you a little bit more sense of what BigQuery ML is, in the next slide here, we have an overview of the kinds of models that are supported in BigQuery ML. So depending on the kinds of use cases, you may consider classification to predict something, regression to predict a continuous or quantitative variable. There are other models as well that are supported in BigQuery ML, like k-means clustering, and we'll talk about time series forecasting. There's also recommendation systems, and if you ever want to import TensorFlow models to run on its data stored in BigQuery, or if you ever want to export your models that you created in SQL in BigQuery outside, you could also do that as well. So in this next slide, you can see we're just going to focus here on time series forecasting. So with that, I think we'll bring it back to Stephanie. Stephanie is going to give us a walkthrough of how it actually works in BigQuery ML. So Stephanie?
Thank you very much, Polong. Yeah, so hopefully that gave you a really good quick overview of what BigQuery does and also what BigQuery ML does on a very high level. So now we can take a look at how specifically BigQuery ML could help in action. One of the most popular use cases of time series forecasting is demand forecasting, like we mentioned earlier. For retail businesses, like I said before, right, there is a Goldilocks problem when it comes to inventory. You don't want to stock too little inventory because that could mean a loss of potential revenue, but you also don't want to stock too much inventory because that could mean surplus of goods taking up your precious storage space with a limited lifespan. So hopefully this slide picks some of your interest if you're falling asleep. Let's take a look at a real life example to see how we can forecast liquor demand with BigQuery ML. As we go through this example step by step, you will also see how easily this pattern can actually be applied to many other use cases in retail industry or medicine, right? Like prescription medication, demand forecast, etc. So before we jump into modeling and training, all that good stuff, let's first take a look at our data. Right, so here we are using the BigQuery public data set on liquor sales in the state of Iowa in the United States. So we can see here that the data set contains transactional information on when liquor products like whiskey, rye, and rum, other kinds of liquor are sold in the state of Iowa in the US, and how many bottles were sold in this in the particular transaction. So we can forecast the total demand for each type of liquor over time across all the stores where they're sold. So over here on the box on the left-hand side, right, is how the raw training data looks like when we run the select statement down below over here. right? We have a date column, an item name column indicating what type of liquor it is. And in this case, we're looking at Black Velvet, right? And we also have a total amount sold column over here that is computed. So notice that there are some missing dates between January 7th and January 11th, right? This is fine because the values will actually be filled in by BigQuery ML using local linear interpolation. So here, we're running a create or replace model statement. So with this one single create or replace model query, as you run it, BigQuery ML will actually be creating up to 42 models for each of the individual items time series. And the time series ID column over here, which maps to item name, allows you to train multiple time series models in a single query. So one for every item name in our data. So we don't have to write separate query to train a separate model for each of these products, which can help you save quite a bit of time. And among those potentially 42 models that we train, BigQuery ML will actually choose the best one for each item automatically using auto Arima. So with say 1 million products in total, that's up to 42 million models being created and tested behind the scenes. And then we're returning to you only the best models, one for each of your 1 million products. And that's all within this one single query run. And I also want to explain quickly what this holiday region parameter does over here. So this field allows us to account for holiday effects given your location when doing the time series modeling in BigQuery ML. So by default, holiday effects modeling is disabled. However, we can turn it on by specifying it. And also if we have at least 1 year's worth of daily data. And with this holiday effect enabled, spikes and dips that appear during the holidays of this year will be considered in our forecast as well. So this is what we see when we run that query. So again, these 5 models are the best models that BigQuery ML chose using the Auto Arima algorithm from up to 42 models for each time series. So the non-seasonal P, non-seasonal D, and non-seasonal Q, as well as the has drift columns, define this time series model. The log likelihood, AIC, and variance columns are relevant to the model fitting process. I'm sure you're somewhat familiar with that. And over here, it looks like it's determined the demand for each type of liquor has a weekly seasonality, which means customers exhibit spikes in purchases on a weekly basis. And this makes sense because people probably drink more and party more on the weekends, and therefore they buy more alcohol. That's great. So we train the model, and now we're ready to use it to make a demand forecast for future dates. So this is how the tabular data will look like once the forecast is made using BigQuery ML. Although this is only showing Black Velvet for 5 days, the full forecast results are going to be there for each type of liquor for however many units of days that you specify. So over here, we specify 30 days, and we'll see that very quickly. To make this forecast and to see the results we saw earlier, we simply have to run this SQL statement with the ml.forecast function. And we pass in 2 very important values, horizon and confidence level. So I will go quickly into what each value means. The horizon, which is the number of time points to predict in the future, allows you to specify up to a maximum of 1,000 data points. So in our case, given the daily data, we are putting down 30, which means 1 month of forecasted values. The confidence level over here is the percentage of future values that fall in the prediction interval. So I know this may be a little bit harder to comprehend, so we will jump into that very quickly. But before, exactly what confidence level does, but before we do that, I think the next question you may want to ask is, how do we know if this forecast is actually accurate, right? So the way we can verify that is by plotting the forecast out. We can compare the forecasted values to the actual values, since this all happened in the past, so we can verify the accuracy. And to visualize this, we plotted the forecasted values in orange over here, and the actual values in green on this graph. Hopefully that's easy to see for you. And we also included the historical data to show and see how well the BigQuery ML forecast function performed. And as we can see over here, for the most part, the actual values fell within the 90% confidence level. So what does it mean when we say confidence level? Just to make the confidence level a little bit easier to understand, here are 3 forecasts at 3 different confidence levels for the same model. So at 0.80, your confidence levels are tighter, or say closer to the forecasted values, so that the buffer is narrower. And down here at 0.99 confidence interval, the confidence interval is much looser. So you can be really confident to say that whatever the actual value will be, that will most likely fall within the confidence level. And note that over here, regardless of what the confidence level actually is, the forecasted values will remain the same. So I guess you may wonder, how do I choose an appropriate confidence interval, right? So that is really entirely up to you and your use case. Do you want to be very, very certain that the actual demand will fall within your predicted range? So in that case, right, you may want to go for a higher confidence level, like 0.99 or 0.9, so that your value will fall within that range. Or do you want to really have slightly narrower predicted range to help you better optimize your products and resources? So that will lead you to a lower confidence level, which is something like 0.80. And now you may be wondering, this is also simple and very easy to do, but what is really happening under the hood? So I'm going to pass on to Polong to talk a little bit more about that.
Thanks, Stephanie. So the model that we saw here is called Arima Plus, and it's created by the product team at Google, focused on BigQuery ML. It's actually based off of an internal forecasting system. So by exposing it to users, you can now kind of leverage some of the same technologies that are used internally for some of the services that you may have seen or heard of before. So some of the features that Arima Plus kind of capitalize on is that number one, if you have lots and lots of items that you want to forecast within a single query, you can actually do all these forecasts at once. So up to 500,000 items in a single query, and you can make a forecast for each of those items afterwards by using some very simple queries that Stephanie had showed you as well. Now, because it's built within BigQuery, everything can auto-scale for you. So what that means is when you train your forecasting model, your Arima Plus model, you don't have to, again, figure out, do I need to spin up a cluster? Do I need to have enough CPUs? Do I need to reserve certain GPUs or extra computational resources? You don't have to worry about that at all, because within BigQuery, it'll auto-scale directly for you. It does a lot of pre-processing. Stephanie did mention a little bit around missing values. It also handles outliers, and as Stephanie also mentioned, some holiday effects. There's also some other things that are happening behind the scenes, which I'll go into a little bit. For example, step changes. And here I'll give you a bit of an example of what step changes actually looks like. So here's an example where we saw a big spike in some data that's available in the public BigQuery public datasets. And this particular BigQuery public dataset is on Wikipedia page views. So you can also query this yourself if you'd like to. The one thing I focused on was there a spike in the number of page views for Wikipedia titles containing the term sanitizer? And as we can imagine, at the beginning of the pandemic, and even perhaps till now, you'd imagine that maybe a lot of people are thinking about how to sanitize their hands or how to sanitize, their homes or anything outdoors as well. So the searches for sanitizer on Wikipedia seem to have really tremendously spiked around, what does it say here? 2020, around March time, right? And then it started to fall down a little bit. And yet, even until, let's say, 2021, beginning of 2021, on the right-hand side, you can see in this second red line, there's still a bit of a sustained increase in interest in sanitizer. So above and beyond what it was, all the way up until the beginning of the pandemic, which was essentially beginning of 2020. So we have this, big spike. So we have low visits. First of all, these are daily visits, low visits, and then we have this major spike in interest in sanitizer for Wikipedia page views, and then it decreases fairly sharply, and then it sustains that level over time after the pandemic. So, throughout, I guess now it's not really after the pandemic, so to speak. So what we can kind of sort of call this the pre-pandemic levels, and then sort of like the during pandemic, or the spike during the spike levels, and then kind of at the end, we'll kind of just roughly say it's post-pandemic, but even though it's not really the best nomenclature there. So in the next slide, what we tried was we trained the model first, just on the data up until the beginning of the pandemic. So 2020, January 1st, kind of that's cut off. We trained it there, and the next slide we kind of zoom in a little bit on exactly what the forecasts look like. And of course, no surprise, it's not going to be able to predict these major spikes, because of course it's trying to infer based off of the training data, which has never shown any sort of spikes in sanitizer page views up until the beginning of the pandemic. So of course it's going to forecast as if it's going to continue as normal over the past 2 years, which is the duration of the training data. Now, the interesting thing is, if we go to the next slide, is if we were to run a typical time series forecast model and use for the training data all the data from before the pandemic to during the pandemic to after, well, I guess after the pandemic, after the spike, you'll find that this is based off of a 95% confidence interval. The forecasting model is completely unable to forecast future kind of visits for the sanitizer page views. And then the reason why is because of step changes. That's one of the major reasons, is because suddenly we have this big spike, and then we have this sustained level of sustained level of visits from before to after, that's no longer able to reconcile exactly how to best predict for the next coming timestamps. So with Arima Plus, what it actually does in the next slide here is you can actually automatically monitor the step changes. What that means is the original level followed by the levels that kind of again change during the spike, and also the sustained increase as well, kind of after the spike. So it will account for all these kind of sustained changes. And you can see here, this is the zoomed in view where it is actually able to make appropriate forecasts even after the sustained increase in page views for hand sanitizer. Now, if you were to do this kind of manually yourself using your own kind of favorite frameworks for time series forecasting, you may have to plug in a lot of, extra code and a lot of extra work to be able to make this happen and automatically detect all these step changes. But with Arima Plus, it'll do it automatically for you by default. So you can essentially not have to worry so much about any major changes that may have happened that could have resulted from, major things that happen economically around the world, things that may have, changed for your users or your visitors or your customers or whomever it may be. It'll account for all these kind of sustained changes. So Arima Plus does this out of the box for you, making things quite a bit easier, in my mind, for a person who's really interested in doing forecasts very quickly and kind of being able to do it at scale as well. So with all these changes and spikes and things in mind, I wanted to cover this kind of next section on time series anomaly detection. And Stephanie will give a quick kind of overview here on some of the different kinds of use cases that we might see with time series specific anomaly detection.
Yeah, thank you very much, Polong. Anomaly detection is really all about finding patterns of interest that deviate from expected behavior within your data set. So the ultimate goal of anomaly detection is not just an algorithm or a working model. I'm sure you're familiar. Instead, it's really about getting the value of insights that anomalies can provide. So what does that mean? So that is for a bank, perhaps the number of customers protected from fraudulent transactions. For a tech company, money saved from preventing software intrusions. For a business, money made from perhaps anticipating sudden demand changes. And in medicine, earlier detection or easier treatment. So this is why it's really critical for us to be able to respond very quickly to anomalies. And if your data is already in BigQuery, that's going to be very easy to do. So I think Polong next will show us exactly how we can accomplish anomaly detection very easily with Arima Plus.
Now, as Stephanie mentioned, there's two kinds of use cases. When it comes to anomaly detection for time series, there's kind of when you want to look forward to see if there's any anomalies that may occur in the future, but you may also want to investigate anomalies that occur kind of in the past as well, just to see and check to see if, based off of all of my data and based off all the patterns in demand or patterns in viewership or patterns in something else, have there been any unusual activities that have occurred historically versus those that are still incoming and new? So on the one hand, one is more like retrospective, and you're trying to understand the past. Whereas the other one is you're trying to detect anomalies almost kind of very quickly, so you can respond to them and make appropriate, behavioral responses. Whether it's to, in a store, stock more of this particular item that's highly in demand, unusually high in demand. Maybe it's, there's a post on social media that made everyone really interested in that particular product, and you didn't quite notice it, but based off of the time series forecast, it can detect the anomaly that has occurred, the spike in demand that has occurred. And so that is an anomaly in new data. So these are the two things that you can kind of observe. Now, in the next slide, you can kind of see here how Arima Plus can be quickly used to detect anomalies, both historically and also for new data. So I say historical, but it's basically based off of the data that it was trained on. So in the first kind of section on the left-hand side here, you'll see select star from ML.detect anomalies. You pass in the model that you had simply trained using Arima Plus, and then you also pass in the probability threshold, which I'll kind of explain in a little bit. And essentially, using the model and the threshold that you want, it'll give you a true or false for each of the historical timestamps and their values, and whether or not it kind of identifies those historical timestamps as anomalous. So that's in the past or based off of the training data. And then for the forward-looking anomaly detection, this is where you are adding in some new data. So here in the green text here, we're adding in a table, mydataset.mynewData, or whatever your table may be called, and it's now detecting anomalies based off of the model that you've trained, based off of the threshold that you want to provide, and then now applying that on new data to detect if there's any unusual spikes or unusual dips that go above and beyond the probability threshold. If it goes above that threshold of here 0.8, it will return a true for that particular row in your data. So let's kind of see the actual what that actually would look like, Stephanie, in the next slide. You can see here there's a column called is anomaly, and it's a true or false. It's a Boolean column, and you can see there's one row here where it's detected that value for that time series data is true. It's considered an anomaly, and it's because that value, that time series data, 22,326, falls above, actually above and below the lower and upper bound values in the prediction interval. So the anomaly probability here for that particular timestamp is 0.96, which happens to be greater than this particular threshold at this time when I actually use 0.95, not 0.8, 0.95. It went above 0.95 here, so it's deemed to be anomalous. So from here, you can run extra SQL statements. If you want to do a where is anomaly is equal to true, or and if you want to run that just to filter for which of those timestamps in the future or in the past were anomalous, you could quickly check which ones were anomalies and maybe investigate further or try to figure out how to respond as quickly as possible to any kind of unusual spikes in dips that may happen after you've trained the model. So with that, I think Stephanie, as a next step, is going to kind of talk about an important problem of trying to keep your model sort of up to date. So Stephanie?
Yeah, thank you very much, Polong. So like Polong mentioned, right, once we have the models ready, everything works perfectly. We're able to do time series forecasting and anomaly detection. We may start wondering about ways to easily orchestrate these models so that we can easily retrain them and we don't have to do a lot of additional manual work to ensure that our models are up to date. And BigQuery ML definitely got that covered and is making it quite easy to do. And the most straightforward way, in my opinion, is to use the scheduled queries, right? So if you are like many businesses that need to create fresh time series forecasts based on the most recent data, and I'm sure that's a very common use case, we can use the scheduled queries to automatically rerun our SQL queries that we wrote before. And that could include the create or replace model statement, the ML.forecast statement, etc. And we can set how often we want to rerun these queries and whether we want to start on a certain day and end on a certain day, and you have control of that as well. And even send out email notifications when these are run, or pops up messages to carry out further actions downstream. Once you've scheduled it, this is how it's going to look like for you, and you can very easily keep track of all the scheduled query jobs. However, that's not the only way. There are also other more advanced ways to do something similar with Cloud Composer, if you're familiar with Cloud Composer. So yeah, with that, I think we have come to an end of our presentation. So I have included a short link of a Google form in case you have additional questions or feedback on maybe BigQuery ML and whether you're interested in giving it a try, maybe what functionalities you're looking at and how we can improve our product as well. We're very happy to take those feedback from you. And so just let us know. And yeah, thank you very much again for taking the time to join us on the talk today. The pleasure is all ours. And we really hope that you were able to have a few takeaways from it. If you have any further questions, please feel free to reach out to me or Polong after this presentation. We'll be very happy to talk with you. And again, thank you so much for your time.
Thank you very much. And you can also ask questions. Confer has established a Slack kind of a group. So feel free to ask us questions there or reach out to us directly on social media. But as Stephanie mentioned, pleasure to speak to all of you, and hope you have learned a thing or two today. Thank you.
Thank you.